Now let's look at set of discussions as far as the partial differential equations are concerned. So now we are looking at solution by the Lagrange method. Earlier, when we were trying to form the partial differential equation, we did confront situations like this. That is, you had a function which in turn depended on two relations u and v. Now, the solution of the Lagrange, the partial differential equation by Lagrange method is to achieve exactly this. There, we started with this function and formed the PDE, but now it is the other way around. We would insert with the PDE and arrive at this. That means our endeavor is to arrive at these two relations. That is, relations between x, y, z using the following. What is step number 1 in order to do this? Compare this with the standard equation, because here you have the coefficient of p. When I say small p, it is the partial of z with respect to x. The coefficient of q, when I say that, it is the partial of z with respect to y, and then the r. So that can be written in the following form, that is in the form of ratios. Now you have the first ratio, it is dx by x square minus y square minus z square. That's equal to dy divided by 2xy, coefficient of q, and then dz by r, which is the 2xc, right? So this is the standard form in which you will have to write. This is step number 1. Any problem given, this is invariably the procedure. First identify your coefficient of p, coefficient of q, and then the r. So these three ratios have to be written down. So this is step number 1. Now obviously I am looking for two relations u and v. What you got to do is you have to apply your basic calculus and look for that relationship amongst these ratios. If not possible, these ratios have to be manipulated to produce that relationship. So because we require two, one of them that seems obvious is using these two. Why? Because if you looked at these two, x is common. If you cancel x, what happens? Dy by y and dz by z, which can be easily integrated, and you can get a relationship between y and z, and you would be fulfilling one of the requirements, right? So that is, I mean, if you consider these two fractions, you have a complex function you cannot integrate, right? So that is why I cannot consider equating the first ratio with the second, or first ratio with the third. All that I can do, what is very, very obvious, is equate the second ratio with the third ratio. You must always identify such opportunities so that you can establish one of the functions. Here, don't you see that the second and the third ratios are obvious? If I cancel 2x, I get dy by y, dz by z, which can be easily integrated, and you get a relationship between y and z. So therefore, what I would do is, I'm going to attempt step 2 as, can I use any two ratios to arrive at one of the relations, so that I'm partially fulfilling this particular function, right? So I'm going to use these two here, and the reason is very, very obvious. So once I use these two, what I will get? I will get dy by y, and that's equal to dz by z. 2x get cancelled. Now if I integrate both sides, what I will get? I will get log y, that's equal to log z plus a constant. Now can I simplify this further? This can be written as log y by z, because if I bring log z to the LHS, it is log y minus log z. By basic logarithmic algebra, it is y by z of log, that's equal to constant. And if I take log out, that is, this can be written as y by z e power c, that means that is also a constant. and let me introduce one more constant, k. That means my first relationship is arrived at. First relationship is arrived at. So why? I could equate, the first step is obvious for every partial differential equation. This is what you got to write. But in that, you identify two ratios, potential ratios, which can give you a relationship between y and z, or y, z, x, whatever. In this, it was very convenient to get a relationship between y and z. So therefore, my function is partially filled. That means if I'm talking about here, y by z is partially filled. Now I will have to find out this. So step number one, let me reiterate. Step number one is to write this standard formula, or standard set of ratios, I would say, standard set of ratios, and identify any two ratios potentially to give you this. Sometimes you may not get ratios, you may have to actually struggle with all the three and arrive at one particular ratio, but fortunately in this case these two ratios could be obviously equated, simplified to get a relationship. Now let's come to the second relationship. How do you arrive at it? Again, look at the ratios rigorously. What you have here is dx by x square minus y square z square, that is equal to dy by 2xy, that's equal to dz by 2xz, right? So this is standard set of ratios. Now one more thing that you can do always, this is a fact of basic algebra. You can multiply all the denominators. Let's say you are going to multiply this by k1, this by k2, this by k3, and the corresponding numerators also can be multiplied by k1, k2, k3, and then you can produce a new ratio. So one of the techniques is exploit the given ratios. If you cannot exploit beyond certain point, only two we could exploit, then you can form one more ratio so that you can exploit the ratios further. So I'm going to produce one more ratio. I'm not doing anything extraordinarily different. I'm using all these and producing one more ratio, and that ratio always will have the following form. Remember this carefully. k1 dx, k1 can be x, y, 1 by x square, 1 by y. We'll have to reason that out. Here I'm just giving you the general formula. Then we are choosing the appropriate k1, k2, k3. How it works is that you are going to get one more ratio, that is k3 dz, and then in the denominator you will get k1 into x square minus y square minus, of course it is minus z square, plus k2 into 2xy plus k3 into 2xc, right? So this is going to be one more ratio, and I can equate with any of the ratios to get one more relationship. So now tell me what exactly should be k1, k2, k3 so that I can equate with any one of these, and then I would be able to get one more relationship. That requires some amount of analytical thinking. It is not very, very obvious. For example, one of the choices could be x, y, z. One of the choices could be x, y, z. How exactly it plays out? You can see when I make the choice for k1 as x, k2 for y, k3 as z, that's one of the things that I want you to try. And sometimes it becomes very, very obvious, 1 by x square, 1 by y square, 1 by z square. Sometimes it will be 1 by x, 1 by y, 1 by z. Here it appears that 1 by x, y, z would work, because you can see here you have got minus y square minus z square terms here. The moment I multiply this by y, 2y square x, 2z square x, and add it to this, multiply this throughout by x square, I will be able to get x square plus y square plus z square in the denominator. And also I can equate that with this, the one extra x whatever I am going to get, equate with this, I get rid of that one extra x, and this 2 can go to the numerator, and the numerator would have the following form: 2x dx, 2y dy plus 2z dz. So if I get rid of this x, this would simply be, if you integrate, it would be log of x square plus y square plus z square. So with that idea, what I can do now is I can choose k1 is equal to x, k2 is equal to y, and k3 is equal to z. Let us see whether it works or not. Now multiply this by x. What you will get? You will get x cube y square x minus z square x. Let us see. X cube minus y square x minus z square x. Now multiply the second by y. You will get xy square plus z, the last term, by, and you can see clearly minus y square x, there is 2, that becomes, it is plus y square x. So there is 2xz square, there is minus, if you add it up, you will get xz square. So that means if you take out x, you exactly get x square, y square, z square. So it is quite logical that you first try with x, y, z, then you try with 1 by x, 1 by y, 1 by z. I mean, depending on the situation. But here, looking at the terms, it becomes very, very obvious that you try with x, y, and z, so that you get this standard function and x can be taken out. And when you equate with one of the ratios, x can be cancelled. And in the numerator also, you will have dx into x, dy into y, dz into z, and this too, when transferred to that, it becomes easily integrable. That is, it can be easily integrated, right, to get your final ratio. So therefore I have got one more ratio that is taking into account k1 to be x, k2 to be y, k3 to be z. So if I write my set of ratios, now it's going to be, now dx by x square minus y square minus z square, that's equal to dy by 2xy, that's equal to dz by 2xz. Now my one more ratio, now by taking x as k1, y as k2, z as k3, what did I do? I achieved one more ratio. And what is that going to be? It's simply going to be x taken out, x square plus y square plus z square. And since I'll have to multiply all the numerators also, it's going to be x dx plus y dy plus z dz. Correct? That's very, very easy. Now what I have done, I have generated one more ratio. So what did I do? I first used the given ratios. I could equate the last two ratios and get a relationship. That doesn't suffice. I need one more relationship. So what should I do? I should generate one more ratio. Step number 1, write all the ratios, get one relationship if possible. Otherwise, you will have to generate more ratios. Now I have decided to generate one more ratio to get one more relationship. And what was that? Multiply each term by x, y, z respectively, and then generate one more ratio. And that's what I exactly did. I multiplied this by x, this by y, this by z, added up, I got this, and in the numerator I got this. And you can clearly see, if I equate that with this or this, I can use any one of them. Let me choose the second one. So what I get here is, when I equate that, I get 2xy, that's equal to x dx plus y dy plus z dz divided by x into x square plus y square plus z square. Look at the opportunity here. X would get cancelled, 2 will go to the numerator, and you can see here in the denominator you have x square plus y square plus z square. In the numerator you have 2x plus 2y plus 2z. That means it is simply going to be, when you integrate, log of x square plus y square plus z square. And here also you get dy by y. That means if you integrate, it is log y. So therefore it becomes very, very useful. I'll cancel this and then bring this 2 to this side. So what I would have here is, by generating that extra ratio, I have the advantage of generating one more relationship. That is, I have x square plus y square plus z square, and here I bring this 2 to here, so I get 2x dx plus 2y dy and plus 2z dz. So this will give me what? This will give me log of x square plus y square plus z square, right? Plus a constant, and that is equal to log y. You can see here, when I differentiate this, I get 2x dx, 2y dy, 2z dz, which is exactly in the numerator. So this becomes log of x square plus y square plus z square. So if I simplify, I'll get y by x square plus y square plus z square, because when I bring it to the LHS, it can be written as log of y by this term, that's equal to constant. So if I take out log, that becomes one more constant, let us say k2, I have one more relationship. So now, previously I developed this relationship. Now I have developed this relationship. So finally, my solution would be phi of y by z comma y by x square plus y square plus z square, that's equal to 0. So this is how I actually end my solution. You can clearly see here. So this is what I exactly started with. These are the 3 standard ratios. First, you will have to identify the coefficient of p, write it below dx. Identify the coefficient of q, write it down dy. Identify r and write it down dz. 3 ratios you will get. Exploit any 2 ratios to get a relationship. What we did, we exploited these 2 ratios because it is quite obvious xx and 2 get cancelled, and you can integrate to get log y, log z plus constant. That means you have a relationship between y and z. What do we have to do next? We will have to generate one more ratio to get one more relationship. That can be done algebraically. You can multiply the first term by k1, second by k2, k3, and it applies to numerator terms also. So you will be able to generate one more ratio. So that means we have started with these 3 ratios, and I used k1 is equal to x, k2 is equal to y, and k3 is equal to z, and generated one more ratio. That was step number 2. First, write the 3 ratios, manipulate those 2 ratios, get a relationship. For the second relationship, you may have to generate one more ratio, and that ratio is generated like this. And the advantage of that ratio is, you will see that xx would get cancelled, and 2 when brought to the numerator, you can clearly see that it gives you this situation. So if you differentiate the denominator, you'll get the numerator. So that means when you integrate this, you'll get log of x square plus y square plus z square, that's equal to y. So you can get a relationship between y, x, y and z, that's equal to k2. So both your relations are arrived at. And also you can you'll have to be very, very observant. We said, since it is x square minus y square z square, and there is a positive term here, positive term here, when you multiply that by x square, y, and this by z, you get y square z square. X can be taken common, and that would leave you with x square plus y square plus z square. And also, the very idea of taking x out will work, because if you equate with either this ratio or this ratio, xx would get eliminated, and what you are going to have is this, which when you integrate, you'll get log of x square plus y square z square, and one of these ratios also can be integrated because you're going to get log y. So therefore, what we did is, we did consider one more ratio, and equating that ratio with either second or third ratio, you'll be able to get this relationship. So both relationships have been got. So finally, this becomes my solution. So once again, the first step is to write the 3 relations. That is 3 ratios. If you can manipulate and get a relationship, fine. Otherwise, generate one more ratio or one more ratio. Sometimes maybe 4 or 5 ratios, and from that you will be able to arrive at the relationship which, when written in this form, forms the solution of the partial differential equation. So let's move on and look at more discussions. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.